leaves of the independent. So symmetric means basically it tells you that there is some redundancy in the system. If you say that the system has some symmetry, right? So that means, for instance, if you look at something like this, right? Now, if I give you a lattice of this form and I ask you to generate a lattice which has an arbitrary number of rows and columns, right? I ask you to generate an n by n lattice, right? It is sufficient for me to provide you with only two vectors, right? It is enough to provide these two basis vectors, right? So if this is the vector is A, this is B, let's say, right? Then you can use these two vectors and you can find the coordinates of any other point, right? By multiplying by the integer labels of that point, right? So to generate this lattice, I don't have to specify the coordinates of every single point, right? I only need to provide you with these two vectors and the size of the lattice that I would like to have, right? So this is possible, right? Because there is a certain symmetry. What is the symmetry? It's a translational symmetry. Right? So that means if I translate either if I am at a given if I am, let's say, at a given point R and I make a translation, right, to some point which is given by some coordinates which are integer multiples of these two basis vectors, right? So then the lattice at this point will look the same as it does at this point, right? So I have translational symmetry, right? And we would describe this symmetry in terms of two generators. We would say that there are two generators. So one is the generator of translations along the A vector, and the other is the translation along the B vector. Right? So we would say that this whole lattice can be generated by two generators, TA and TB, right? Now, if I have some lattice point R, right, then what is the action of this generator of TA? It will take R and translate it by one integer step along the A vector. Similarly, right? And if you want to be complete, you would say that you also have have the inverse generators, and you also have the identity element. The identity element doesn't do anything, right? It just keeps things the same. So this is, now let's say that I have some function, right? So this could be like a wave function. It could be, if I have some system on this lattice, like let's say I have this lattice describes there are electrons on the lattice. Right? So for instance, how would I describe the state of the system? I would describe it as in terms of some wave function, right? And this wave function has to have the same symmetries as this lattice. Right? So first of all, so these generators, they take anything, right, and shift it by these vectors. So if I take these generators and I act on any function, what will this give me? Okay? So if I take this and multiply and act on this thing any times, what will this give me? This will give me. Okay? This is the reasoning which leads to. Have you all studied Bloch's theorem? You all should have encountered it in condensed matter or solid state or both. Right? So Bloch's theorem says that if you have a system which is defined on some lattice which has some periodic symmetries, right? Then the wave function of that system can be written in terms of some state that is defined entirely in one single cell, right? Times some exponential function. Once you know the value of the state in this single cell, right, that you know it for the whole system. So, or if I know the value of the wave function at this point, I can translate to this cell, I can translate to this cell, right? To find the wave function here or at this point. So once I know the state in this cell, I know everything. So this is possible because the system has a redundancy. Right? So what is the meaning of redundant? Means that you have more information than is needed to provide a complete description of the physical properties of the system. Right? So this is this is one example. Now, what we are interested in, we want to talk about relativistic systems. So relativistic systems means that systems which are defined on spacetime. Right? So what is spacetime? Well, spacetime is sort of like a lattice. Only difference is that these numbers, they need not be integers. They can be arbitrarily real numbers, right? Because at the level of the description that we are using, space-time is smooth, right? It's a continuum, right? So if I have 3 plus 1 dimensions, right? And I want to again use this kind of a language, let's say, then how many generators would I have?
Maybe 3 plus 1 generators.
Huh?
3 plus 1 generators.
Meaning how many is that?
4.
4. Right? So I would have four generators, right? 3 would be generators of spatial translations. 1 would be a generator of time translation. Right? And so this would give me, so now we're talking about R31. Okay? R31 denotes space, 3 space dimensions and 1 time dimension. Okay? Now, just to remind you all, for those of you who have not taken one of my classes, or maybe in the first year, I taught you guys something. Huh? Seminars. Okay, so those who, since you have not, all of you have not had a class with me, just want to remind you again that if you have any questions at any point, okay, Rahul, and next to you is Sumit, and behind Hirasita is Pankaj. What? Sorry? Malikarjun. That sounds nothing, absolutely nothing is perfect. Malikarjun. And then I have the usual suspects. Few people are not here. I think Gajendra. Is Gajendra still like I think he's here, right? Huh? He will come. Right now he is in West Day. माता के दर्शन करके and then Faria, I guess maybe she's still upset at him from yesterday. Is there anybody else I'm missing out? Anasuya, who I said, and I want to teacher. Who else is not here? Huh? Kiran. Kiran. She attending some Vipassana retreat somewhere. Vipassana, you know what Vipassana is? Never mind. But you need to find out in all these YouTube. So for everybody who has or has not attended class, please ask me a question at any point. And just because you might have attended my GR class, that doesn't mean that if you ask me a question, that I'll be like, oh, I taught you this in GR, why don't you know it? It's okay, I don't expect that level of commitment from anybody. My assumption is that at the end of the semester you do a clean wipe, and so you can ask me any question, okay? So this is what we normally refer to as our space-time. So three space dimensions and one time dimension, right? And by the same reasoning, there will be four generators of translations, three spatial directions and one time dimension, right? So let us write down all those translations. Let's give them some names. Okay? Px, Py, Pz, and Pt. Okay? These are four generators. So right now, I have not told you what form this generator takes, right? You can just think of it as some abstract machine. You take anything, you put it in this machine, right? It takes that object, shifts it, gives you the answer. That's it, right? So these are just some machine. What they look like exactly, we'll see later. But this does not complete the list of symmetries of space-time, right? Space-time has more symmetries. What are those symmetries that are missing? Rotations. Alexander, you're with me? Following? There are any questions you ask me, okay? So these are translations. We need rotations. How many rotations are there? How many? Four. Somebody said four. Spatial rotations, right? Better word rotation here. Only around the space axis. So there are three such rotations. Again, we can write them as these are our translations. These are the rotations, right? So if I give you some object, some function, let's say psi or r, right? And I take, let's say, Jz, okay? And there will be some parameter theta, okay? So like in this case, these were discrete. Here we have a discrete symmetry, right? So the discrete symmetry, so I have a discrete number, either n or n. These are continuous symmetries, so I have some continuous index, right? So what will this do? So take the system and rotate it around the z axis by an angle theta, right? So if I take this, you give me some r prime, psi of r prime, right? Where what is the relation between r and r prime? Is if I say that these are my coordinate axes and this is the vector r, right? Then this angle here is theta and this guy rotates r around the z axis and gives me, so I'll make this theta really big so that you end up over here somewhere and I get r prime. So is this taking it, rotating it? Okay. So this is this symmetry of the system. generator would act on any function. Okay? Any function. You take it to this. But I have not said what sort of function are we talking about, right? What sort of system are we talking about? The system, right, this need not represent anything which has rotational symmetry. This is just an arbitrary function. Right? Now, if I have a system, or if I have a quantum state of some system, which is translationally or rotationally invariant, right? What effect would this generator have on this state? It would leave it invariant, right? At most you would get some this state Jz acting on psi of r, it will be some lambda times psi of x. Right? So this Jz, so what does this equation remind you of? This is a looks like an eigenvalue, right? Now, and in this case, what sort of lambda can you have? What will be the form of the lambda? It will be some sort of a phase, right? E to the I, some theta z. Sorry. E to the I, e to the I theta. Okay? So, we have translation, we have rotations. Does this complete the list of symmetries of spacetime? No. Right? We have three more symmetries, three more generators. Those are the what we call, so we are normally in the text we find them as labeled as A's, A's, and these are known as the boosts, right? So what is a boost? Boost is a change in the velocity of the system, right? So what is the action of the boost do? If you have some point now, so these boosts, rotations act only on spatial coordinates. These spatial translations act only on spatial coordinates. This time translation acts only on the time coordinate. Right? Boosts are rotations. Right? And now a rotation, by the way, normally we have this picture of a rotation as being around some axis, right? But that picture is not quite correct, because if you are, let's say, in 4 dimensions, right? And you say that there is a rotation. So rotations, the simplest rotations, okay, the elementary rotations, are not around an axis, but they are instead in a plane. Right? So if you take any 3-dimensional rotation, for instance, you can break it up into a combination of rotations in either the xy plane or the yz plane or the zx plane. Right? Now in 3 dimensions, it so happens that if I have the xy plane, a rotation in the xy plane is equivalent to saying that there is a rotation around the z-axis. Because there is one z-axis, you mean z-axis is perpendicular to the next one. But if I have more than one axis, let's say I have 4 dimensions or 5 dimensions, then I can still give a meaning to the rotation in the xy plane. But now I can no longer say that this rotation is around the z-axis or around the t-axis. Okay? So the proper way to write down these rotations would be jxy, jyz, and jzx. It is in 3 dimensions that we have this duality between vectors and planes. Right? If there is a plane, there is a unique vector component. The same way, these boosts are rotations in the xt plane, the yt plane, and the zt plane. Right? So again, the table, that is the way they are conventionally written down is x, y, right? But the time axis is always involved. Now, so these are the set of symmetries of Minkowski space. Okay. Now you might say that, well, can you think of any other possible symmetries of Minkowski space? Scaling, yeah. You could take any coordinate, right? You could take any coordinate and scale it, right? So you would have a expansion or a contraction. Anything else? Anything which is not covered here? You could also have what in this thing complex analysis you refer to as inversions, or in two-dimensional Euclidean geometry we call them inversion, right? So an inversion takes, we have, let's say you have some circle. An inversion maps all the points outside the circle into the circle, all the points inside the circle outside the circle, right? So something like this. If you have a complex number z, take 1 by z as a inversion, right? It will map infinity to 0 and 0 to 2. So you could have inversions in the xt plane, yt plane, z plane. You could have, right? Or in the xy plane. Then you could also have some sort of transformation. So let's say that you start with you have two. Let's say you think of these two as pieces of. So here two pieces of chalk. So you could have a transformation which changes things like this, right? So if you have some sort of a spatial element, it is transformed like in this form, right? So it's called a shear, right? And if you combine, you could combine shears and scaling and inversions and all of these. All right. So the complete set of symmetries would include translations, rotations, boosts, scaling, inversions, right, and shearing, or any combination of these. Okay.
So what about the reflexes?
Reflections, that's true. Reflections are also possible, absolutely. Reflections are also possible in symmetry. So yeah, reflections, right? Those are additional possible set of symmetries. Okay. So now we won't be studying all of this. Okay. We will be studying a subset. We will be studying the subset that is associated with these generators: translation, succession, and boost. Okay? So there is no squeezing or expansion or any twisting or shading. Or there could be discrete symmetries, but that depends on the system. So that is something that we will talk about later, like parity, when we talk about solutions of different Hamiltonians. So now, these are the generators, right? Now the thing is, what do they generate? So these are generators, right? And you have seen these in many different forms, right? They will maybe not called by the same terminology. So for instance, this P of x, right? What would it would be something like this, right? This is a momentum operator. I have not put an h bar. You can always put it because I just want to talk about a generator like in general, a translation. Now, what do these generators do? They generate these. So, how if I take this quantity, right? If I want to act on some state and I want to make that state move forward by some distance delta x along the x-axis. Okay, so for simplicity, I'll just look at P of x. So I have some state psi of, so again, psi of x, some function, arbitrary function. I want to take this function and I want to shift it by some amount delta x. Okay? How do I describe this? This can be written in this way. E to the e to the I, so not to the I, e to the delta x px, okay, times psi of x. Right? Now, this might look, have you seen this expression in some courses? Has anybody written? Maybe you have. Maybe you got lost in the sand of time. But you can see that this will give you this expression, and it's very easy to see how you just expand this. Right? So if you have e to some exponential of some quantity, right? A can be anything. It can be a matrix, it can be a number, it can be an operator. Right? I'm writing it here, boldface one. Right? This is the. So if you take this and put in this quantity here, delta x dx. Okay? You get 1 plus delta x dx is dx plus delta x squared by 2 factorial dx squared. Now you want to be careful. For instance, here when I am writing down delta x, when I am writing down the second order term, I am doing this, right? So what is this? This is delta x dx and delta x dx. Okay? And px is something that will act on both delta x and on this one. Okay? But this will not be affected, delta x will not be affected by px, so we can just move it through. That's why we can write it as delta x squared times px squared. Okay? So whenever you look at such products of operators, you always have to be careful. And so on, right? This is the expansion of this exponential operator. Right? If I take this quantity and act on psi of x, right? What will that give me? It will just give me the Taylor series expansion of this quantity. It will just give me, first term will be psi of x, the second term is delta x, delta x squared, dx squared psi by 2 factorial. This is the Taylor expansion of psi. Right? So, a derivation, right? This is a not the derivation of a proof, but a derivation as in taking the derivative with respect to some quantity, gives you the operator which generates translations by that. Right? So now all of this talk about symmetries. How does it make our life? We want to do physics, no? We don't want to like show how clever we are, right? That's not the goal, right? The goal is to understand some basic concepts, right? So how does this help us understand some basic concepts? So what is momentum? When we say that a system has momentum, right? How we say that it has a or angular momentum. That means that there is some conserved quantity. So you have some system, system can undergo some evolution. It can change from point to point, either in space or in time. But if there is some quantity that remains constant, you call that a conserved quantity, right? And then you can say that, well, the value of this conserved quantity is either my momentum or my energy or whatever. Right? So if I say that I have a particle that is moving in the x-axis, right? So the system, I say, has some momentum along the x direction, right? That's because the system looks the same at every point along the x-axis, right? And how am I generating these translations from point to point? I'll generate them using some operator. This is true whether you are in classical or quantum, it doesn't matter, right? There is nothing quantum about it. So, when you want to go to quantum mechanics or classical mechanics, right? So now you don't necessarily have the system defined at one point, right? You have to talk about operators, expectation values. So then the natural question to ask is that if I have some system and I want to talk about its momentum, let's say, then momentum will be some operator. What operator should it be? Right? So the operator corresponding to momentum has to be this quantity. Right? What is, because this quantity generates shifts in that direction. Right? Similarly, like this, same way I can write down the operator, the momentum, the time momentum, right? So to speak. Right? That will be something of this form. PP will be something like this, right? What is this correspond to in quantum? Huh? Corresponds to the energy of the system. Right? Now if I take all three of the spatial momenta and the energy, what do I get? I get E, Px, Py and Pz, right? Energy and the, so now I'm using small expression to denote the fact that these are numbers, right? And these numbers are they arbitrary? Like if you are talking again about a particle, some particle with mass, are these numbers completely arbitrary? Can I just take any four numbers and put them here? Can I take any combination of E and P? Will all combinations be valid? Right? So let's say that let me set two of these momenta to 0 for simplicity, okay? And this is E and this is P of x. Is any point in this described give me a physical state? There is a restriction, right? What is that restriction? That restriction is right? This is the restriction, right? This is the restriction on that watch is available. Anybody who can revive it? We have been waiting for a hero. Sort of like King Arthur. You know King Arthur? There was a sword called Excalibur, and this boy came along, and there was a sword was stuck in stone, right? And everybody tried to pull that sword out of the stone. One boy came along, he pulled it out. Then he became King Arthur. If you can be like that, you can be the king or the queen who started this watch. Okay? We can call this watch Excalibur. I'm serious, please man, this is a watch.
It's confusing.
Huh?
It's confusing.
What?
If it is stuck like that, it is confusing. That's what I said.
What is confusing?
No, if your watch is stuck like that, then it
There's
is
nothing confusing about it. What is confusing?
Okay. I think I didn't put my words.
It's confusing. It's not working. There's nothing that's doing. Okay, so this is this relationship, right? If you look at this, again, you forget about y and z for the time being. This tells you that e squared minus px squared c squared is equal to n squared c to the fourth power, right? Then this corresponds to certain, this gives you a set of points. That set of points is this is the equation of a hyperbola, right? Some x y a whole square minus y by b whole square is equal to c square. Right? So this is the equation that a relativistic particle of mass m satisfies. Okay? Now, since we have learned so much about operators, right? And how they generate these quantities. So instead of writing down this as an equation between numbers, I can write it down as an operator equation. So instead of the quantity E, I replace it with the operator E, which is what I h bar dt. Instead of the operator P, I replace it by the operator P, which is minus I, right? What is it? Okay. If you get confused, just say h bar equal to 1 and just say you're working in natural numbers. If you put these expressions back in here, right? You get this squared is minus h bar squared dt squared. This squared is minus plus minus minus plus c squared h bar squared del squared, right? If you take p to be the gradient, you take the square of that, you get del square, right? Del x square plus del bar. And this is equal to n square c4, right? But now this is an operator equation, right? So an operator needs to act on something. let's say this something is a function of some spatial coordinates. So then the operator version of this expression will tell you that this operator acting on this f is equal to n square c4 acting on f. Okay? This can be written as minus h bar squared or h bar squared and minus dt squared plus del squared with the factor of c squared. Okay? Actually, you can take the c square and divide by dt square by c square and bring the factor of c square. Okay? What this does is, if you take d by dt divided by c, you get something that is units of d by dx. Right? So what are the units of d by dx? What are the dimensions of d by dx? Huh? 1 by l, l inverse. What are the dimensions of d by dt? T inverse. So if I take 1 by c d by dt, I get 1 by c d, which is l inverse. So then everything inside this has the same units. Times this function f equal to n squared f. This quantity you can write it as box. Okay. So box. So the box operator is what? It's actually a vector operator, which is equal to 1 by c dt and dt. So it has four components: d by dt, dx, dy, dz. If you take del squared, that gives you this times itself dot product. That will give you minus 1 by c square dt squared plus. Okay. What is this also known as? This expression? This expression is known as the Klein-Gordon equation. Okay. Now, if you look at the syllabus, Klein-Gordon equation is something that is comes at the end of the course. Do you have a class after this? Is there a class after this? Huh? Okay. So this is a, and what kind of equation? This is a wave equation. Right? And to derive this equation, what was the basic input we used? We used the concept of symmetry. Once you understand how to write symmetry generators, all of the equations of physics come out very easily. Okay? So this is what makes symmetry such a powerful thing. In fact, you can solve the Hamiltonian of this thing, the hydrogen atom, without going through all of that hypergeometric function nonsense. If you keep in mind that a hydrogen atom describes a system which is spherically symmetric, right? You start with two objects, two massive bodies, big M and small m, with some Coulomb attraction. You write down the Hamiltonian between these two objects. You have a kinetic term for both of the objects, and you have a potential term. Then you can change to the center of mass coordinates. When you change to the center of mass coordinates, right, the Hamiltonian becomes a product. It becomes a product of the center of mass term and a orbital term. That orbital term is what we call the Schrodinger Hamiltonian of a hydrogen. That only depends on one position. That Hamiltonian is spherically symmetric. I can apply. So, what does it mean that something is spherically symmetric? It means that if you take these angular momentum operators and take the commutator of these angular momentum operators with the Hamiltonian, you get symmetry. So then, this tells you right away, if it is not immediately clear to you that this is the condition for something to be symmetric with respect to some generators, don't worry, we'll come back to that later. Right? Alright. And so this expression tells you that if you have some state j of h psi, that is equal to h of j psi, right? And if psi is a solution of the Hamiltonian, then I can write this h of psi as some number e. So I can bring that number out, right? Let's say lambda. So I get lambda j psi is equal to h times j psi. Okay? But this is again an eigenvalue equation. J psi is some other state, let's say psi prime. So what this expression is telling me is that j psi is some psi prime. This expression is telling me that h, operator h acting on the psi prime, this gives me an eigenstate of my Hamiltonian. Right? So if I want to find eigenstates of my Hamiltonian, what do I need to do? I need to find states which are eigenstates of the Hamiltonian. States which are spherically symmetric. Those states are very easy to write down because the angular momentum operator breaks up into three parts. One part gives you this phase around the z-axis. The other two components give you the angular momentum L, whose solutions of that equation are the Legendre polynomials. So the wave functions are Legendre polynomials multiplied by some phase factor. Right? Anyways, I think I should stop there. Hopefully this may